Here we have two conducting spheres connected by a conducting wire. These spheres are sufficiently far apart so that the potential around the left sphere is given by kqa over Ra, and the potential around the right sphere will be kqb over Rb. We also see that the radius of A is 1/2 of the radius of B. First of all, how do the electric potentials compare for these spheres? So one thing we have to know about conductors is, for electrostatic situations, points in a conductor that are in contact are going to be at the same potential. You could think of the potential as spreading out among the entire conductor surface. And I'll represent this with an equipotential. So what we find is whatever potential is on the surface of sphere A will actually match the potential on the surface of sphere B. It'll be the same inside the conducting wire. And not only that, but when it comes to conductors, we said before that the electric field inside the conductors would be 0. And that's true. However, the potential is not 0. However, the potential inside is not 0. The potential will still be V throughout the conductor. So that's one difference between potential and electric field. So let's say that VA equals VB because the conductors are in contact and they're in electrostatic equilibrium. How would the charge on each sphere compare? Well, now what we can do is we can substitute in for VA and VB the formulas that we were given. So let's put KQA over RA on the left, and we'll put KQB over RB on the right. We also see that radius A is 1/2 of radius B. We see that we can cancel the constants. And since RA equals 1/2 RB, since we have this, we can replace RA with 1/2 RB. All right, so we see that the radii here can cancel. We would want to multiply the 1/2 to the other side, revealing that the charge on A is actually 1/2 the charge on B. All right, so if we've got charge QB on sphere B, then we will have 1/2 of that amount of charge on sphere A. Now, at a first glance, it might seem like that makes sense, that the smaller sphere should have less charge. And just for the purposes of drawing, let's put a positive charge around them just so that we can see it. We want half as much on this sphere. So I had 8 pluses on sphere B, so I would want 4 pluses on sphere A. It may seem at first like it's proportional, but we can't neglect the three-dimensional nature of spheres here. How do the surface charge densities compare? Are they the same? Well, you might think that since their potentials are the same, the surface charge densities are the same. But is that really true? So for that calculation, we're going to want the total charge on A divided by the area of A. But I'd really like to get it in terms of B's values. So if I can just replace charge QA with 1/2 QB, I'll also replace the surface area of A with 4 times pi times its radius squared. I'll make one more substitution because I don't want things in terms of A. I want them in terms of B so that I can compare the two. I'll do 1/2 QB over 4 pi. And now let's plug in the fact that the radius of A is 1/2 the radius of B. All right, so we square that. CRB squared. We can cancel these, and we'll get 1/2 QB over pi RB squared. That is an expression for the surface charge density of A. And now let's compare it to the surface charge density of B. Well, that would simply be the charge on B divided by 4 pi times the radius of B squared. So interestingly, if we compare the quantities that we got, which one's actually bigger? The surface charge density of A or the surface charge density of B? The answer is the surface charge density of A is twice as much because it's 1/2 QB over pi r squared, and this one's 1/4 QB over pi r squared. So twice the surface charge density. It works out that more charge goes on the surface of this guy. And we all know that conductors will spread their surface charge out because the surface charge wants to get away from itself, basically. So that has important implications when it comes to the surface charge distribution on conductors. If we have an irregularly shaped object with some very large surface areas and then some very tight corners here, we're going to find that there is a higher charge density at the corners. Over here we'll have a lower charge density. It's certainly related to the radius of the points on the surface of the conductor. See here we've got a very tight radius, small curves. So we're going to have a larger surface charge here and a smaller surface charge here.